Welcome to this tutorial dedicated to the TIA Connect test bench. We will discover how to write automated tests for a PLC program, execute them on a simulated PLC, and validate that the logic works even before commissioning. This is the principle of test-driven development, applied to industrial automation. In the software world, automated testing is a standard practice. You write a test, verify that it fails, write the code, and verify that it passes. In automation, this practice is still rare. However, a bug in a PLC program can have serious consequences: production downtime, hardware damage, or even danger to people. The TIA Connect test bench allows you to write test cases in JSON, execute them on a simulated PLC via PLCSim Advanced, and automatically verify that the outputs match expectations. Let's see how this works in practice. We are creating a new TIA portal project with an S7-1500 CPU. We are using an article number in version v1, as this is what PLCSim Advanced expects for simulation. We are creating our motor control function block. It has 3 inputs: start, stop, and fault acknowledgement. And 3 outputs: motor running, fault active, and ready. The logic is intentionally simple so that we can focus on the tests. We create the instance DB and call our FB in the main organization block, OB1. After compilation, our program is ready to be tested. But before downloading, we will first think about what we want to verify. We start PLCSim Advanced and create a simulation instance. This instance will behave exactly like a real S7-1500 CPU, but is software on our workstation. Free for 21 days, without a license. We enable simulation support, download our program, and start the CPU. The simulator is now executing our logic in real time. Our tests will run against this instance. Here is our first test. We define a test case in JSON with a name, a description, and the name of the targeted PLCSim instance. The setup initializes all inputs to false. The first step verifies the initial state: motor stopped, no fault, ready. The second step activates the start and verifies that the motor switches to running. The teardown resets the inputs to 0. Notice the structure: it is clear, readable, and reproducible. Nous exécutons notre test. Le banc de test est connecté au simulateur, écrit les valeurs du setup, puis execute chaque étape dans l'ordre, écriture des tags, attente, lecture et verification des assertions. Regardons les résultats. Chaque assertion est évaluée individuellement, on sait exactement ce que passe et ce que ne passe pas. Deuxième test, l'arrêt. Le setup met le moteur en marche. La première étape confirme qu'il tourne. La deuxième étape active l'arrêt et vérifie que le moteur est arrêté repasse en mode prêt. Chaque test est indépendant et se suffit à lui-même. Third test, and it is a safety test. We force an active fault, then we attempt to start. The motor must not start. This is exactly the type of verification that can prevent an accident on a real installation. If this test fails, it means our safety logic is faulty. Fourth test, fault acknowledgement. We first check that the fault is present and that the motor is not ready. Then we activate the acknowledgement and check that the fault disappears and the motor becomes ready again. This fault acknowledgement cycle is fundamental in automation. Fifth and final test, stop priority. What happens if start and stop are active at the same time? The motor must not start. This is an elementary safety rule: stop always has priority. This test formally verifies it. Let's look at the list of all our saved tests. 5 test cases, each verifying a specific behavior of our motor control: start, stop, fault blocking, acknowledgement, and stop priority. Now, we run the entire suite at once. The asterisk means all tests. The test bench executes them one by one, in order, with setup and teardown for each. Let's look at the summary. We see the total number of tests, how many passed, how many failed, and the details of each assertion. This is exactly the type of report you would expect from a software testing framework, but for a PLC. To better visualize what is actually happening in the CPU, we will create a watch table and go online. This will allow us to observe the bits changing state live during the execution of our automated tests. We are now connecting online with the simulated PLC. By running our tests again, we will be able to see the state changes reflected instantly in our watch table. Let's now rerun the entire test suite to verify our logic while observing the PLC in real time. This time, we were able to visually confirm that our PLC responded correctly to every command sent by the test bench. This testing approach is a valuable time saver for commissioning. Let's recap what we have just achieved. We created a TIA portal project with a motor control FB. We launched a PLCSim Advanced simulator, downloaded the program, and wrote 5 test cases covering essential scenarios: start, stop, fault, acknowledgement, and safety priority. Each test is a JSON file, versionable, reproducible, and automatable. We executed the complete suite and obtained a detailed report. This is the beginning of test-driven development for automation. In a real-world context, these tests would be integrated into a continuous integration pipeline, executed with every program modification. No more "it worked before, I don't know what changed." Thank you for following this tutorial. See you soon on TIA Connect.